To introduce our keynote speaker, may I call on our moderator for this session, academician and fellow of the Samahang Pisika ng Pilipinas, Dr. Cesar Saloma.
Good morning, everyone. The first keynote speech of this conference is by academician Dr. Jose B. Cruz Jr. Dr. Cruz is a control theorist and a professor emeritus at the University of Illinois at Urbana-Champaign, at the University of California, Irvine, and at the Ohio State University. He is a member of the National Academy of Science and Technology Philippines, the U.S. National Academy of Engineering, and a fellow of the American Association for the Advancement of Science, and the Institute of Electrical and Electronics Engineers, the International Federation of Automatic Control, and the American Society for Engineering Education. Academician Cruz received his Bachelor of Science degree in Electrical Engineering from the University of the Philippines, Diliman in 1953, his Master of Science degree from the Massachusetts Institute of Technology in 1956, and his Doctor of Philosophy degree from the University of Illinois at Urbana-Champaign in 1959, all degrees in electrical engineering. Let us welcome academician Dr. Jose Cruz.
Good morning, everyone. The title of my presentation is Complexity Issues in Engineering Systems. However, the theme of this conference, Pagtanglaw sa Pandemya sa Lente ng Pisika, will be reflected throughout my presentation. As you will soon hear, I have made substantial revision and refocused my presentation almost entirely to the theme of the conference. It is a departure from the abstract published a few months ago. Permit me to make some broad definitions pertinent to my talk. Physics and engineering. Physics and other natural sciences can be described as observation of nature and development of a theory to explain and predict the observation. Engineering is creation of devices, systems, or processes utilizing science and mathematics, leading to new technology for the benefit of society. On the other hand, although physicists and engineers are nominally associated with the practice of physics and engineering, in fact, their activities are much broader and wider in scope. For example, John Bardeen had been professor of physics and electrical engineering at the University of Illinois. He won the Nobel Prize in Physics twice, in 1956 for co-inventing the transistor, in 1972 for co-developing a theory of superconductivity. Nick Holonyak has been professor of electrical engineering at Illinois. He was Bardeen's first student in electrical engineering. He invented the light-emitting diode. It has been my privilege and good fortune to have been on the same faculty in electrical engineering at Illinois many years ago. Jack Kilby graduated with a Bachelor of Science in Electrical Engineering from Illinois. He received the Nobel Prize in Physics in 2000 for inventing integrated circuits. He did not have a PhD. I also met him many years ago through many alumni meetings. Finally, there is a book by James, physicist, Nichols, engineer, and Phillips, mathematician, called The Theory of Servomechanisms, published as Volume 25 in the MIT Radiation Series Laboratory. So, may I reword the theme of the conference slightly so that my talk would fit better the theme of this conference. View of pandemics from the lens of physicists. I invite the participants of SPP 2020 as physicists, other natural scientists, to team up with social scientists, policymakers, and engineers to control the complex pandemic coronavirus. So now let us address the theme of this conference. Science-based model to start with. Science mathematical model of the coronavirus is based on observations of the actual society and observation of the environment, as we will describe shortly. Kermack and McKendrick were first to publish a mathematical model of the spread of disease in a paper published in the Proceedings of the Royal Society of London in 1927. Their model was called the SIR model. They divided society or population, N, into three compartments. S representing susceptible, I representing infected, and R representing removed. Actually, there are two parts to removed. One is recovered or free of infection, and a small one called D or deceased. However, let us stick to the original model SIR. So S, I, and R are normalized by the population N, yielding in lowercase S plus I plus R equals 1. So although there are three variables, only two are independent. So their models are described by the following equations. ds dt, or rate of change in time of susceptible, equals minus beta si. And dr dt, rate of change of removed, is equal to gamma I, where beta and gamma are proportionality constants. Note that the first equation is nonlinear because of the product Si. Now the third equation, di dt, is actually derived by equating it to minus ds dt minus dr dt, yielding beta Si minus gamma I. So we choose S and I as state variables. So what are some current interventions in science models of the pandemic? First, as I said before, observations are made and the model, the mathematical model, is calibrated using observations of the output as well as of the environment. So if there is an exponential increase in infected, the usual approach is to increase measures such as wearing of masks, more of those, more isolation to quarantine, and much more social distancing, for example. So if we linearize the original model, the original science model, we have the equations indicated where I naught, S naught are the initial values of infected and susceptible. The third equation, the third differential equation, is not linearized. It is already linear. So if we look at the first two differential equations and obtain the characteristic equation given in the third line to the right, we have the usual quadratic polynomial set equal to 0, and the normal notation for such quadratics is lambda squared plus b lambda plus c equals 0. After some algebraic simplifications, the final criterion, whether we have exponential growth or not, is to check whether the expression beta times 1 minus 2 naught minus r naught minus d naught, close parenthesis, is greater than gamma. Typically, I naught is close to 0, so it is approximated as 0, and likewise, r naught and d naught are 0. In that case, beta over gamma greater than 1 is an indicator of instability. And beta over gamma is usually denoted by the symbol R naught, the most popular parameter in the modeling of the spread of disease. So, what is the usual intervention? If there is exponential growth, then there would be an increase in the interventions or remedies, such as I said earlier, quarantine or wearing of self-distancing and wearing of masks. So, because of the possible recurrence of the virus every time we remove the intervention, we now look at a possible way to make an improvement on that science model. So, what is the first step in extending the science model to what we will call engineered models? This first step is to create stimuli or inputs to the science model. So this first step is to create inputs as indicated in the block diagram. Previously, there was only an output arrow. This time we have an input arrow as well. In this presentation, I will describe a brand new model from Batangas State University being announced publicly for the first time here. The variables we considered are as susceptible, I infected as before, F tested free of virus or recovered, and D deceased. So we have 4 variables, and as before, we normalize with respect to the population N, yielding the lowercase equation S plus I plus F plus D equals 1. So among the 4 variables, only 3 are independent. And so we choose S, I, and F as state variables. Note the main difference between the science model and our new model is the addition of an input z. What is the nature of z? The input z, when scaled up to z times n, is the number of persons per day that we wish to decrease the infection by. It is equal to a nonlinear function of actual infected I and actual susceptible S per day. It could be implemented by modulating the testing, tracing, sending infected to hospitals or quarantine, and wearing of masks. So, what is the second step in creating this extension of science models to engineered models? The second step is to apply control theory to construct the input. As you can see from the diagram, there is an arrow from the output to what we now call controller, and the controller constructs the input Z based on the measurement. This is called closed loop control. So how did we choose Z in the Batangas State model? We use a nonlinear Z. It is B, a parameter, times Si, therefore quadratic, plus 2 or 3 terms that are really linear in S. So B is a parameter at the disposal of the designer, and we will choose it to match one of the betas, our nominal design. The symbols S sub D represents the desired asymptote of susceptible at our disposal, we choose. And I sub D is our desired target for the asymptote of infected. So these are specified by the designer. Clearly, if beta is not known, beta minus B may or may not be equal to 0. So substituting the proposed Z into the state equations, we have these 4 differential equations. Note that the difference between these equations and the science model is the presence of parameters B, K1, and K2. We also have design parameters S sub D and I sub D. Otherwise, if you remove all of these, it collapses to the original science model. So for today, we have the following data in the simulation that I will show. The initial values of I, F, S, and D are given, the constraint being the sum of I, F, S, and D should be 1, and it is. We will try 4 different values of beta, 2, 3, 4, and 5, but we will choose B and K1 and K2 accordingly from 1 for one of the betas. Secondly, we choose the targets SD, ID, FD, and DD. Again, they should sum up to 1. So if you substitute the Z as we proposed for B equals 3 and beta equals 3, or for any beta, we choose one of them and set B to match it, assuming it's known. Then the system becomes linear, and the characteristic equation is as given on the third line. Note that there is no beta in that equation, only K1, K2, and gamma. Gamma is given, K1 and K2 are to be chosen by the designer. Using our standard notation again, for quadratic, the coefficient for the linear lambda is denoted by B, and the constant part of that quadratic is denoted by C. So clearly, it is almost trivial to solve for K1 and K2, given any B and given any C. So, as I indicated earlier, we will choose B capital to be 3, lowercase b to be 3, lowercase c to be 0.2, and K1 and K2 are then solved for, as indicated. So let me show you a graph of I infected. The solid curve corresponds to beta equals 3, our design beta choice as a baseline. Note that it drops exponentially and asymptotically to 0. The important thing to note here is that there are 3 other curves for unknown betas, namely 2, 4, and 5. And all of them drop exponentially, indicating that the system has been stabilized. Next, we show you a graph of F, free of infection. Note that F is the integral of I times some proportionality constant. And since I is exponentially decaying, these integrals are, as indicated, asymptotic to some constant desired level. Finally, I show you a graph of S for the 4 different betas. You will see a horizontal line right at the approximate population of the Philippines. All 4 are on that line, and that's because all those deviations are only in the thousands, whereas S is in the millions. So you will not see any deviation. So what are the advantages of closed-loop policy interventions? Firstly, robustness against wide discrepancies in modeling uncertainties, such as transmissivity parameters. Secondly, only minor adjustments in closed-loop policy would be needed for applications elsewhere, anywhere in the world. So minor adjustments in the choice of B, K1, K2, and the targets. Finally, this closed-loop policy intervention is capable of stabilizing any dynamic system from control theory. In conclusion, I state the following. The Batangas State closed-loop policy model for the suppression of COVID-19 has been publicly presented here for the first time. Next step, collaborate to convince policymakers and IITF to agree to implement the suggested closed-loop policy in order to experimentally verify the model in the Philippines. Finally, the closed-loop policy model presented here can be readily extended to more complex models, such as SEIR, where E stands for exposed, with several layers as described in reference 3 by Chen et al. From Wuhan, China, with many more compartments of the population at various layers. I wish to thank Dr. Tirso A. Ronquillo, President of Batangas State University, and my 8 students in my graduate class on Modern Control Theory and Applications, who are also co-authors in reference 6. Here are the references for the record. Three is Chen et al. From Wuhan, China. 4 is a paper utilizing the model in 3 to check experimentally whether it works or not. Here's the reference to our paper that is to be submitted for review to Philippine Science Letters. Reference 7 is a highly cited paper on the use of adaptive controllers for feedback linearizable systems. The feedback may be nonlinear, but the final effect is to linearize the system. Thank you for your attention.
In your model, in the Batangas State University model, is it able to account for possible herd immunity?
That is possible, but as you know, if we rely on natural herd immunity, it will mean more than half of the population will have to get sick first. And then there will be, in the United States, for example, with 300 million population, more than 100 billion will be exposed and many in the millions would die. So the only reason for going for herd immunity, if we introduce vaccines, where you can provide antibodies in people without making them sick. And so it's a different kind of herd immunity, but that is coming, and we will address that very shortly, where we would add another input for vaccines.
Thank you po. Any other question for Academician Cruz?
Good morning, Academician Jose Cruz.
Good morning po.
This is Valerie Sampson from the DOST.
Opo.
You've mentioned that you hope that these models will be able to reach our policymakers. So
Yes.
this is like a policy issue with the IATF. Does the IATF really have a session? Do they have such meetings wherein they're able to take scientists and see what these models can give in the COVID-19 prediction?
I'm not very familiar, and I will seek NAST and DOST assistance in allowing us to make a presentation so that they may consider allowing such a modification of the interventions they are now applying. And so at an appropriate time, hopefully that will be allowable. And although I'm in the United States now because of the COVID lockdown, I will not be able to go there unless it's Zoom. But I can assure you that President Ronquillo of Batangas State University can make a presentation there as well. So I will definitely ask DOST, NASD, and maybe others in concert, as well as SPP for that matter, because we need collaboration across the board.
Maraming salamat, Dr. Samson, at maraming salamat po, Academician Cruz.
Samahang Pisika ng Pilipinas presents this certificate of recognition to Academician Jose B. Cruz Jr. for sharing his expertise as keynote speaker on complexity issues in engineered systems during the 38th Samahang Pisika ng Pilipinas Physics Conference and Annual Meeting with the theme Pagtanglaw sa Pandemya sa Lente ng Pisika, held online from 19 to 23 of October 2020. Given this 19th day of October 2020, signed Cyril S. Salang, Secretary General, and Percival Almoro, President. Thank you
very much.
Academician Cruz.
Thank you very much, Academician Cruz.
And thank you very much for this.
Thank you.